to Pankti's tutorial. This video lecture is about one of the classification of signals, and that is continuous and discrete time signals. To define a continuous time signal is a signal that will have some value at every instant of time. Suppose on x-axis we have time, and this time is in unit minutes, and this is the place where the time value is 0. Then this continuous time signal will have some value when the time is 1 minute. It will have some value when the time is 1 second. And if I go into more minute details of this signal, it will even have some value for 0.1 second or 0.01 second. That means for a continuous time signal, if we go into very minute details, we can find out its value at every time instant. But when we talk about a discrete time signal will have some value at particular instance of time, and at other instances of time, the value of this signal remains undefined. Discrete time signals are actually obtained from the continuous time signal by a process that is called as uniform sampling. Let us now look at that uniform sampling through these waveforms. From this continuous time signal, if I take samples at uniform interval of time, then we get a signal which is like this, and this signal is then called as a discrete time signal, and that uniform interval of time after which I am taking the sample is called as the sampling period. So here, if this signal is ft, it is getting transformed to a signal which is, so here I am denoting it with fnts, because we have the value at every nts instant of time, and that n here denotes an integer. So when we are taking samples from a continuous time signal, we are changing ft to fnts. Now if we take samples after every 1 unit of time, then we can substitute here ts is equal to 1, and then the form that we will be getting will be fn. So generally a discrete time signal is denoted as fn because it will have some value at every n instant of time where n is an integer, and a continuous time signal is denoted by ft. So ft here is denoting the continuous time signal, and fn here is denoting the discrete time signal. The important point to remember here is the argument t of ft can have any real number. For example, it can have the value 5 by 2, 3 by 2 and so on. But when you talk about the argument n of fn, it can only take the integer value. Now this is the graphical form of representation of the discrete time signal. Let us see how this discrete time signal can be given in the form of an equation. Suppose we have a discrete time signal which is like this in the form of the waveform, and the values are given here. The signal has these values at these time instants. So let us now see how the equation can be formed for these values and this graphical form of the signal. So in this equation, I have given all the values that fn can take. It has got value -2 at time instant n is equal to -2. It has a value 1 for n is equal to -1. It has a value 2 for n is equal to 0. The next value it has is -1 for n is equal to 1. And the next is 2 for n is equal to 2. When we are writing the equation, we consider only the values at which the discrete time signal is non-zero. So for all these values, the discrete time signal is non-zero. So here I have given it in the form of an equation, but this equation does not tell us that at what time instant what is the value of the signal. So what do we do here is we add an arrow mark, and the arrow mark is added at the place where the value corresponds to n is equal to 0 time instant. So when n is equal to 0, the value that we have here is 2. So this is that value. Therefore, we have added an arrow here to represent n is equal to 0 time instant. All the values that are left to this arrow mark would be pertaining to the time instant with negative integer values, and all the values that are right to this arrow mark will be corresponding to the positive integer values of time, and this is how the discrete time signal can be represented in the form of an equation. Thank you for watching the video.